In a previous video, we used a scatter plot to get an approximate regression line equation for predicting the y variable based on the x variable. And we use this actually the same data set with the x variable was the gestation or length of pregnancy in weeks, and the y variable was birth weight in ounces. And we're going to do the more precise way of doing it now. And so the best fitting slope, the slope for the best fitting line is given by this equation here. It's the correlation coefficient r times the standard deviation for y divided by the standard deviation for x. And then the best y-intercept is going to be the mean for y minus the best slope times the mean for x. So before we can use these formulas, we have to compute r, and the most time-consuming part of the process is going to be computing r. So now I'll show you the formula for r. So the correlation coefficient r is this formula here. It looks kind of complicated, but let's try to break it down. Inside parentheses here we have this score for x minus the mean for x divided by the standard deviation for x. So that's the z-score for x. And then inside parentheses here we have the score for y minus the mean for y minus y bar divided by the standard deviation for y. So that's the z-score for y. So what we want to do is compute the z-score for x for each baby, and multiply it by the z-score for y for each baby, add up these products of z-scores, and then we divide by n minus 1. So it's going to be a long procedure, but note here that before we can use this formula, we have to first get the mean and standard deviation of each variable. So that's where we're going to start. We're going to start with getting the mean and standard deviation of each variable. Okay, so this is the same data we had before. Quincy was born after 39 weeks and weighed 104 ounces. Rochelle was born after 40 weeks, weighed 100 ounces. Sophia, born after 32 weeks, weighed 64 ounces, and so forth. So let's first get the mean and standard deviation for x. Okay, so if we add up all these, the total here is 390. So the mean for x is the total of that last column divided by 10. So it's going to be 390 divided by 10, and that's going to equal to 39 weeks. So the mean gestation is 39 weeks, and then we need to then use this formula to get the standard deviation. So we want each score minus the mean. 39 minus 39 is 0. And 0 squared, square that, 0 squared is 0. 40 minus 39 is 1. 1 squared is 1. 32 minus 39 is negative 7. Negative 7 squared is 49. 41 minus 39 is 2. 2 squared is 4. 38 minus 39 is negative 1. Negative 1 squared is 1. 40 minus 39 is 1. 1 squared is 1. 42 minus 39 is 3. 3 squared is 9. 38 minus 39 is negative 1. Negative 1 squared is 1. 41 minus 39 is 2. 2 squared is 4. 39 minus 39 is 0. 0 squared is 0. Let's check. This middle column should add up to 0. I put the 0 down here, but let's just double check. We have the positives. We have 1 plus 2 is 3, plus 1 is 4, plus 3 is 7, plus 2 is 9. The negatives, -7 plus -1 plus -1 and -1. So that checks. Okay, so let's add this column total here. 149 is 50, 55, 56, 65, 66. I get a total of 70 here. Double check. 5, 14, 15, 16, 20, 69, 70. Okay. So the standard deviation is the total of that last column. Well, square root of the total of the last column, which is 70. 10 minus 1 is 9. So square root of 70 over 9. And see what that is. Second square root, 70 divided by 9. I get 2.78 something. 888 66755. Okay. Okay, so that's the mean and standard deviation for x. And then we have to do the same thing for the y variable. So, okay, so these are the y values. I add these up, got a total of 1020. So the mean for y, 1020 divided by 10, which is 102. And then compute the z-scores. Each score minus the mean. 104 minus 102 is 2, and then square it. 2 squared is 4. 100 minus 102 is -2. -2 squared is 4. 64 minus 102 is -38, I guess. -38. -38 squared. 38 times, negative times negative is positive, so I don't have to worry about the sign here. 8 times 8 is 64. Carry the 6. 3 times 8, 24, and 6 is 3. 8 times 3, 24. Carry the 2. 3 and 3 is 9. 2 is 11. 4, 4, 4, 1. 1, 4, 4, 4. 120 minus 102 is 18. 18 squared. 18 times 18. 64. 6. 1 times 8, 8. 14, 18. 324. 92 minus 102, -10. -10 squared is 100. 110 minus 102 is 8. 8 squared is 64. 122 minus 102 is 20. 20 squared is 400. 96 minus 102 is -6. -6 squared, 36. 100 minus 102 is -2. -2 squared is 4. 112 minus 102 is 10. 10 squared is 100. Okay, so let's check. This middle column should total to 0. Let's add the positive. 2 and 18 is 20. 28. 48. I get 58 here. -38, -40, -50, -58. Okay, that's right. Okay, so the last column, let's see. Let's line these up better. We have 4, 4, and 324, 100, 64, 400, 36, 4, 100. Okay, 4 and 4 is 8, 12, 16, 20, 30. Carry the 3. 3 and 4 is 7, 9, 15, 18, carry the 1. 1 and 4 is 5. 8, 9, 13, 14. I get 2480. Double check here. 10, 14, 18, 22, 26, 30. 3, 9, 15, 17, 3, 6, 12, 14, 18, to carry the 1. 1 is 2, 6, 7, 10, 14. Okay, I get 2480. So it's the square root of 2480 divided by 9. And we can do that on a calculator. And second square root 2480 divided by 9. I get 16.599866613. Okay, so that's the standard deviation for y. Okay, let's just double check here. Just double check my answers here before I go much further. Okay, so even for x 2.7. Okay, they look good. Okay, so okay, so now we can go. The next step would be to compute the z-scores, so I've partially filled in this chart here for the z-scores. I left a couple of rows blank. So for Quincy, the z-score for 39 is going to be, let's do Quincy down here. Yeah, I'm going to do it on a different page. Okay, so Quincy, I'll just do this on a different page here. We want xk minus x bar over sx. Okay, so the Quincy score is 39, the mean was 39, standard deviation for x was 2.7888, 66755. And that's going to equal 0. And then the z-score, Quincy's z-score for weight, Quincy's weight was 104, so we want yk minus y bar over sy, and that's going to be 104 minus, the mean was 102, and divided by the standard deviation, which was for y was 16.599866613. Okay, so okay, so let's see what that is. 104 minus 102 equals, divide by second recall, equals, you get 0.12 something, 0.482899. Okay, so we can fill those in on the first row. I filled in the rest of the chart already, but for Quincy, the z-score for x was 0, and the z-score for y was 0.120482,899, and if you multiply those two z-scores together, you get 0. Okay, 0 times 0.12 is 0, and then so I filled in the rest of these, but you would do that for each baby. Compute the z-score for the gestation and the z-score for the weight, and multiply the two z-scores together, and then we want to add these up. Let's see. I get something blocking my screen here. Get that out of the way. Okay, so then we would add those up, and I'd get a total of 8.2 something. So the correlation coefficient is going to be the total of this last column, 8.208262668. Divide, there's 10 babies, 10 minus 1 is 9, so divide by 9. And that will give us the correlation coefficient. So it's 8.208262668 divided by 9. I get 0.91 something. Okay, so that's close to 1. So that's that would indicate a strong positive correlation, close to 1. So it's a strong positive correlation. Between gestation and birth weight. Gestation or length of pregnancy and birth weight. Okay. Okay, so that's the hardest part of the computation, is getting the correlation coefficient. Once you get the correlation coefficient, then there's only a couple of computations to do to get the other statistics that we want to get. Related to the correlation coefficient is the proportion of variability. That's r squared. It's often expressed as percent, but that's the correlation coefficient times itself. So it's r times r, or r to the second power. And if you multiply this out, you get 0.83. 8.31797,235, or it's rounded off as approximately 0.83, and it's often expressed as a percent, so it'd be 83%. And the way that's interpreted is 83% of the variance of birth weight can be explained by gestation, or the length of pregnancy. And the best slope, mathematicians like the letter M for the slope. You've probably seen that if you take an algebra course. Statisticians like the letters A or B for the slope. But anyway, the best slope is the correlation coefficient times the standard deviation for y divided by the standard deviation for x. So it's going to be 0.912029185 times, well, I'm running out of room down there. I'll write down here 0.912 029,185 times the standard deviation for y, which was a 16 point something, 16.5998613 divided by standard deviation for x, which was 2.79. No, 2.7888666755. So the best slope okay, 0.9 something times standard deviation for y, divided by standard deviation for x. I get 5.428. Okay, so that's the best slope. That's ounces per week. And then the best y-intercept, y bar minus a times x bar. So the mean for y, I think was 102, minus the best slope, which is 5.428571428, times the mean for x, which was 39. Okay, so let's go. Okay, so it's 102 minus second recall times 39. We get negative 109. Okay, so that's the best y-intercept for this data set. Okay, so we can then write down the equation, the birth weight, best fitting equation. Birth weight is the 5.42 something times gestation plus the negative 109.7 something. And then if we check the Quincy's predicted birth weight, we just replace gestation with 39. So maybe I'll do this on a separate page. For Quincy's predicted so Quincy's birth weight was 39. So it's going to be 5.428571428 times 39 minus 109.7142857. Okay, so okay, so 5.42 something times 39 and plus a negative 109. Get 102. So Quincy's predicted birth weight, 102 ounces, and then so the residual is a prediction error. Is the actual minus the predicted. So Quincy's actual birth weight was 104. 104 minus 102, which is 2 ounces. So Quincy's prediction error is 2 ounces, and then the squared residual, Quincy squared, this is all for Quincy. Quincy's squared residual, or squared prediction error, 2 squared is 4. Okay, so we can do that for each baby, and so for Quincy, the predicted birth weight was 102. The residual 104 minus 102, which is 2 ounces, and the squared residual is 4 ounces. So if we do that for each baby, and add up the last column, the middle column total should be 0 or close to 0. There might be a little bit off by 0 because of rounding, but this should be pretty close to 0. And then the last column tells us how accurate our predictions are. So it's the total sum of squared errors for 17. And when I tried to do it by hand, using numbers that were not exact, it was further off. This is the best that we can do. It has the best sum of squared errors. It's something called the SSE. The sum of squared errors is 417, and that's the best that we can do. And we can also use the calculator if we put these into the calculator, and you can also get these same numbers here with a lot less work. So you push clear while holding the on button, then clear, second data, right arrow enter, and then put in the data, and then push stat var, push the left arrow 3 times, you get the correlation coefficient R, 0.912 something, push the left arrow again to get negative, the intercept negative 109.71, and push the left arrow again, you get the best slope. So you can use the calculator to check. For the exams and the homework, I'll give you for the exams and the homework are a partially filled in chart, so that because it is a long process, so it kind of shortens the process here. So I would give you a partially filled in chart and then have you complete the chart, so that I see that you know the method without having to go through the complete process from start to finish. If I don't give you a partially filled in chart, then you can well, I'll either give you a partially filled in chart, or have you estimate it from a graph, or if I don't do either of those things, then you can use the stat program on the calculator, because it is a long process. It can also be done on the computer. Some of the questions in the homework and on the exam, I might just give you some computer output and have you identify the features of the that we're looking for from the computer output. So we see the correlation coefficient R 0.912 something, R squared 0.83 something. We have the residual. This is the sum of squared residuals actually, for 17 point something. The intercept negative 109.7 something. This is the slope. They call it x variable 1, but this is actually the slope, the 5.42. So it's sometimes some of the questions you might just see some computer output, and then have to be able to sort of identify what we were looking for from the computer output. And that concludes this presentation.